Hey everybody, this is Mr. Mott. What we're going to do is go through and further examine what was going on in our rule for dissolving lab, where we came up with the rule like dissolves like. Okay, so these are all the structures for the solutes that we had in our lab that we mixed with water and hexane. So taking a look at letter A, that's copper sulfate CuSO4, and then above it we see these charges. Okay, those charges are going to let you know that it's ionic. Okay. And so looking at the structure, that's how you're going to know later on. So we can write ionic because we see the charges. Now later on, we're going to figure out why there are those charges there. It has to do with gaining and losing electrons and a concept called electronegativity. But that's a discussion for a little bit later. If we try to look at what other solutes are ionic, we can look at letter B, which is NaCl. We see the charges above it as well. So this is going to be ionic for the same reason. And letter F, we see these charges above NH4Cl. So all three of these are going to be ionic because we see those charges. Okay. Next comes what happens if we don't see the charges? Well, that means they're going to be polar or nonpolar. And scientists choose this word polar because it's something that's kind of familiar to us, like magnets have poles, or even like consider batteries have a pole, like positive side, negative side. But basically a polar means it's going to mean that one side doesn't look like the other, or it's different than the other. So looking at letter C, we can kind of use symmetry to, if you can't tell just by looking at it, we can look at symmetry. So if we draw a line vertically and say, does the left side look like the right side, or does it have, and so I would say no, it doesn't. So the left side doesn't look like the right side. So therefore this molecule has a pole. Okay, so we're going to say that this molecule is polar. And if we look at it in terms of symmetry, we can say because no lines of symmetry. Now, letter C is methanol. Methanol is a type of alcohol, but that's not the one you would want to have in a drink if you were of age. Methanol is produced from wood, and this stuff will make you go blind and then die, so not a good thing. Okay. Let's look at letter D. This is urea. Urea is found in your urine and a bunch of other things. Drawing a line of symmetry vertically, let's see if we have poles. Well, the left side looks like the right side to me, so I don't think I have a pole in that direction. But what if we look at the top and the bottom? Well, the top and the bottom do not look the same, so therefore they have poles. So I'm going to call this molecule polar. And for the reason, I'm going to say only one line of symmetry. Okay, so you need to look at it sort of from different directions to see if the molecule has poles in some way. Okay. Scrolling to the left there, we look at letter E next. Letter E is what we have for transmission fluid. But the thing with transmission fluid is that it's a mixture of different substances, and the molecules tend to be different even from one manufacturer to the other. So we can't really show you those. Okay. Letter G, we're going to come back to, okay, and letter G is ethanol, and like I said, we're going to come back to it because ethanol is sort of that special case where it was soluble in both water and hexane, and we're going to come back to that. Okay. Letter H is naphthalene. Naphthalene is the main chemical in mothballs, but no moths were harmed in the making of our chemicals and things like that. That's a little bit of a joke if you get it. So let's take a look at lines of symmetry. Okay, so vertically, looks to me like the left side looks like the right-hand side. And then what about the top and the bottom? Well, so if I draw a line of symmetry horizontally, the top looks like the bottom as well. So it looks like we actually have two lines of symmetry here. So there's no real way that we can look at this molecule and say that it has a pole. So therefore, we're going to call it nonpolar. So letter H is going to be nonpolar. And we're going to say because 2 lines of symmetry. Okay, so our rule for, if we kind of put together what we've done so far, our rule is that if we have at least 2 lines of symmetry, then we're going to say that our molecule is going to be nonpolar. But if we have 1 or 0 lines of symmetry, the molecule therefore will have a pole, and we determine the classification is polar. Okay. Looking at water and hexane now. So water has a line of symmetry vertically, meaning the left looks like the right. But if we look at horizontally, the top does not look like the bottom. And so therefore, because we only have 1 line of symmetry, water is polar. And so for our reason, we can write 1 line of symmetry. If you want to pause the video and try a hexane, you can, and see what you come up with for hexane. All right. If you draw your lines of symmetry, the left side looks like the right side, and the top looks like the bottom. So therefore, hexane is considered nonpolar. I guess we already knew these classifications, but maybe just trying to figure out the symmetry on your own is a good exercise. We're going to say nonpolar because 2 lines of symmetry. Okay. And finally, let's come back to ethanol, letter G. Okay. So for ethanol, if we try to just do our lines of symmetry, we're going to see ethanol doesn't have any lines of symmetry. So if I try to draw a line of symmetry this vertically, the left side does not look like the right, so therefore I would determine that it's polar. And we could almost really stop there because that sort of goes along with the classification that we told you. Okay. However, what if we do something like this and we say, okay, let's keep that line of symmetry there, and then let's say that I didn't have this part of the molecule, and instead there was an H here. Okay. All of a sudden, this molecule looks a lot like hexane, and we'd have end up having like 2 lines of symmetry here. And because we have, basically what we have is sort of part of the molecule of ethanol is polar, so it's definitely polar how it's written and what the structure is. But if we had the right-hand side covered up there, then all of a sudden starts to look like hexane, which is nonpolar. So what you have is ethanol being a molecule that exhibits polar tendencies and nonpolar tendencies, and that's why it turns out it's soluble in both water and hexane. And soaps work the same way. Soaps are very, very, very long molecules, where one end of it is polar, and then the rest of it's nonpolar. So that's why soaps are so good at dissolving lots and lots of different types of substances. Okay? Hopefully that helps you understand how to classify molecules. Thanks for watching.